Okay, if I label what I have, I'm told that SV and WQ are equal to each other. Okay, so I find where that is my given. Okay, so I look at the next statement, SQ equals SW plus WQ. So does that fit the structure of segment addition? The sum of the parts equals the whole, so let's test it and see. Here's SQ. Is that equal to the part SW plus WQ? Yes, so that's segment addition. Check the other one as well, SQ, it's the same segment, is equal to the part SV plus the other part VQ. So even though they're separate parts, okay, they still form the segment addition. Okay, when I move to step 3, I have SW plus WQ equals SV plus VQ. So this does not fit the form of segment addition. It does potentially fit the form of adding two values to the same side. So if we had SW or SV equal, or WQ and VQ equal, we could just add equivalent values to those. We don't have those anywhere up above, but we do recognize that these exist somewhere up above. So SW plus WQ exists right here. SV plus VQ exists right here. So when we go back and look at those, are those set equal to the exact same thing? They're both set equal to SQ, the exact same thing. So if two things are equal to the same thing, they're equal to each other is transitive property. Transitive property is always also substitution. Okay, and then we can go to our final step here. And again, usually you build from the previous statement, but if I want SW to equal VQ, okay, when I look back here, I don't have SW or VQ isolated anywhere in my equations. So I'm going to just try to build it off of the previous step. So to get SW alone on one side, I would have to subtract this. To get VQ alone on one side, I'd have to subtract SV. Well, are WQ and SV equivalent values? Based on the givens, they are. So if I remove equals from equals, the remainders are equal is an example of subtraction property. Okay, I can subtract equivalent values from each side, maintain the balance of that equation.